Welcome back, students. In this lecture, we are going to talk about overview of regression analysis. Let's get started. Regression analysis determines the relationship between one dependent variable and a set of independent variables. This sounds a bit complicated, so let's look at these examples. Imagine that you run your own restaurant. You have a waiter who receives tips. The size of those tips usually correlates with the total sum of the meal. The bigger they are, the more expensive the meal was. You have a list of order numbers and tips received. If you try to reconstruct how large each meal was with just the tip data, a dependent variable, this would be an example of a simple linear regression analysis. A similar case would be trying to predict how much the apartment will cost based just on its size. While this estimation is not perfect, a larger apartment will usually cost more than a smaller one. So, regression analysis consists of a set of machine learning methods that allow us to predict a continuous outcome variable y based on the value of one or multiple predictor variables x. Briefly, the goal of regression model is to build a mathematical equation that defines y as a function of the x variable. Next, this equation can be used to predict the outcome y on the basis of new values of the predictor variable x. Simple linear regression use one independent variable to explain or predict the outcome. So basically, we have two types of regression analysis, simple regression and multiple regression. Simple regression use one independent variable to explain or predict the outcome. For example, the example that I used with the tips. The predictions you make with simple regression will usually be rather inaccurate and simple. And therefore, we usually use multiple regression. Unlike simple linear regression, multiple linear regression uses several explanatory variables to predict the dependent outcome of a response variable. So in our case, when we look, for example, at the price of the apartment based on its size, we would add another predictor variable or independent variables, which will be the location of the apartment in the city. And this will be already a multiple regression. So there are also cross-sectional analysis and time series analysis in regression analysis. Cross-sectional analysis refers to the data gathered from the time step period, to the same time period. So when we analyze the data from the same time steps, while time series analysis involves data observed over equally spaced points in time, and then we use regression analysis to analyze those time series data. So basically, regression analysis could be performed in linear regression manner when we are looking at the straight line relationships, and the formula for this is on the slide, or we are looking at nonlinear regressions. So when the relationship between dependent and independent variable cannot be modeled by linear line, so by the line, and we use logarithmic relationships to model such relationship. In some situations, such as the genomic fields, you might have a large multivariate data set containing some correlated predictors. In this case, the information in the original data set can be summarized into a few new variables that are called principal components, that are a linear combination of the original variables. These few principal components can be used to build a linear model which might be more performant for your data. This approach is known as a principal component based method, which include principal component regression and partial least squares regression. An alternative method to simplify a large multivariate model is to use penalized regression, which penalizes the model for having too many variables. The most well-known penalized regression include ridge regression and the lasso regression. Okay, and on this slide, we can see the representation of a linear regression model, which is a linear equation. In this equation, y is a value that we are trying to predict. X is an independent input value. Regarding parameters, B represent the coefficient that every input value is multiplied with. X is independent variable and B0 is intercept. Changing b, so the coefficient impacts the slope of the line, while changing intercept b0 lets one move the line up and down the y-axis. A multiple linear regression models that you can see on this slide look like this. We have also a dependent variable y, that a single variable that we are trying to predict with a regression model. We have independent variables which are denoted by x, that are explanatory variables, also called independent variables or predictors, and they are used to predict the dependent variable. Coefficients B here, beta coefficients are the values computed by the regression tool reflecting explanatory to dependent variables relationships. B0 is an intercept, and here is also a random error term or residuals of the model. Two possible problems arise when we use a multiple regression. They refer to overfitting of the regression model and multicollinearity. So overfitting means that the model you built with a multiple regression becomes too narrow and does not generalize well. It works okay on the training set of your machine learning model, but does not function properly on the items not mentioned before. Multicollinearity describes a situation when there is a correlation between not only the independent variable and the dependent variable, but also between the independent variables themselves. We don't want this to happen because it leads to misleading results for the model. So, to conduct this type of analysis properly, we need to carefully prepare our data and also to check for multicollinearity and overfitting. But don't worry, we are going to cover this in this course. And now I would like to talk about briefly a comparison of the regression model and their validations. So when you have a multiple regression model, you would like to choose the best model. So the best model is defined as a model that has the lowest prediction error term. The most popular metrics for comparing regression models include root mean square error, which measures the model prediction error. It corresponds to the average difference between the observed known value of the outcome and the predicted value by the model. And you can see how this root mean square error is computed. There is also adjusted R-square representing the proportion of variation in your data explained by the model. This corresponds to the overall quality of the model. The higher the adjusted R-square is, the better the model. Note that the above-mentioned metric should be computed on a new test data that has not been used to train the model. But don't worry, we are going to talk about this in detail within our course. One last slide in this introduction to regression modeling lecture, I would like to talk about validation approaches to regression models. One of the most robust and popular approach for estimating a model performance is so-called K-fald cross-validation. It can be applied even on a small data set. K-fald cross-validation works as follows. Firstly, we randomly split the data set into k subsets or k-fold, for example, 5 subsets. Then we reserve one subset and train the model on all other subsets. Then we test the model on the reserved subset and record the prediction error. And then we repeat this process until each of the k subset has served as a test set. Then we finally compute the average of the tick recorded errors. This is called the cross-validation error, serving as a performance metric for the model. This is not only this is only the one approach for validation of regression analysis. You will learn during the course more approaches and different metrics, but I would like to highlight that one because it is one of the most commonly used one. In the following lecture, you will learn about machine learning in R. In the section 3, we will apply different methods for regression analysis, and I will provide you practical